Yo, it's me, Mutant Sam. And now that we're not doing journeys anymore, or I guess we're going back, but I guess I already just posted the debates. So I decided, um, I'm gonna do a couple of like one one video a day of just one attempt on every map. So let's start. I'm probably gonna be in an empty server, and I'm gonna pick Ramses because I'll if I pick Viola, that means I'm sweating, but like my S key is low-key tweaking, so let's not do this. So just gonna be Central Core. We're gonna go Central Core, and then you see the areas on the left? Those are like the hard versions of the maps. We're gonna go like the map, the hard version, another version if it has it. Central Core has a even harder version. Most maps, I think, it's the only map with like two harder versions. And then we'll go one down, and then go to the left area, go down. Not every map has a hard variant, but if it has a hard variant, we'll go through. I only get one attempt on every map, and I'll just try my best to win. If I have time, I'll fit 2 runs into one day, but I'm pretty sure most days will just be one run, depending on like how fast I go and how hard the map is and how long the map is. Any infinite maps, there's only two, and one of them is just a variant of the other. So on the infinite map, there's an you know what? If it's one run, I'll just go until I die, or I'll like stop recording if I can't keep going, and I'll just pick up a bit later. Um, my summer session 1 is about to end for college, so my class is about to end. I'm a few days away from my final exam. It's not really a final. I mean, you can use all the knowledge for it, but it's not necessarily cumulative. It's just on the of the last material uses information from the whole semester, so it's basically a final. I'm in electricity and electricity and magnetism class, so charge in like a particle, electric fields, and Gauss's law. I hate that guy. Not really. It's just like, it bothers me because I sometimes get it wrong and it gets annoying. You know what? Let's talk about Gauss's law just for fun. So Gauss's law is like if we have an imaginary surface, then like all the charge that goes through that surface will equal the integral of like the electric field that goes through it times the area that the electric field is crossing. So like you have like let's say a little charged particle, it's like an electron. Okay, I know it's an electron, bro. Okay, you know it's an electron, and electrons produce an electric field because they have charge. And if you have charge, that means you produce an electric field. Okay. Now, what if you want to find the electric field? Well, um, technically, you could like do the force that the electric field produces times the charge, but like normally you can deal with the force if it's theoretical. So that's out of the picture. Um, and then yeah, if you're like in a class, you'll be given the formula Q over R squared. Is okay. Let's just Q is a charge. Like if an electron has a charge of some coulombs, then you put the charge into Q. That's the first part. R or R squared, but R is the distance from the object, and squared, so if you get further from it, it's over r squared. Over is like denominator of a fraction, so it's like 1 over r squared. So if you get further from the charge, then you're gonna lose electric field strength. So there's gonna be less electric field at that point, and it changes by the square of the charge. So if you go, if you go like, if you increase your distance from the charge particle by 2, so like if I'm here, away, if I'm this far away from this yellow, if okay, if this part of the yellow is that far away from me, I go here. Now it's full away from me. That means the electric field changed by 4 instead of, if I was 3, then that would be changed by 9. But if I increase it by 3, that means it's going to decrease by a factor of 9. It's going to be like divided by 9 because it's dividing by r, not multiplying. Basic lesson, actually, but we're not done. Now, and A, it's kind of constant where, because they were like discovering the formula, but like the units didn't match up, and they were like maybe a billion, they were like literally a billion times off. So it's like, oh guys, we need a K, and they had like a value. So yeah, but and then now for Gauss's law, we can actually like find that again because like for a sphere, like if you put a sphere around it, so you have electric field times dA, like the integral. Okay, maybe not all of you know what an integral is because that's calculus. So like an integral is like you're summing a bunch of little parts of a whole. Like not all of those parts might be the same. That's why you use an integral to sum them up. Like oh, like infinitely tiny parts of it. You sum it all up. Now you have a value. So in this case, it'd be electric field times dA, and so dA is the part where you're summing it all up. dA would be like if you drew a sphere, or if like imagine a sphere particle. So like here you see my character. You imagine a sphere all around me. Then dA would be like a little tiny square on the, or like it wouldn't be a square. It'd be like a curved sheet of paper in a way. But like it gets so tiny that like it's basically flat, like a square. So then you use an infinite amount of those dAs all around the sphere, and then and you sum them up with the integral, and then boom, now you have the flux. That's Gauss's law, and like it's electric field times dA because the electric field is passing through the air, the dA or the sphere, and how if there's more electric field passing through the sphere, that means there's going to be more flux. Now, not all the electric field in the area that's enclosing it, they aren't related every time. So, like you, if you have an integral, like you have EDA, right? Electric field times dA. If electric field isn't really related to like the area of the sphere, uh, then you can actually just take it out of the integral and it'd be like electric field times the integral. So like instead of electric field times dA all in the integral, you can move it out of the integral. So instead of integral E dA like that, you could just have it E times dA because with because like the area that isn't dependent on the electric field, so you're allowed to do that. That's like an integral thing. But how does this bring you back to the electric field formula? Well, another thing about flux is that it also can be represented by the total charge that the sphere or any it doesn't have to be a sphere. It can be any kind of shape, but whatever that's inside of it, the flux, e- the flux equals the charge inside divided by some weird number called epsilon zero. It's like a subscript zero, so it's like the zero is kind of like under it instead of like an exponent where it's like above, like up there, it'd be below, like a period. And you can, and since flux equals that, and electric field dA. Oh, and one more thing, the K thing, it also equals 1 over 4 times pi, not the food, one forever. You know, the one that's kind of related to circle in a way, because like circumference and stuff, or area, times that same epsilon zero. So the area of a circle, well, wait, I mean, the area of a sphere. Wait, aren't spheres like three-dimensional objects? They use volume, right? Well, it's actually the surface area. So, like the surface area across the whole sphere, that would be your K. So, so you have so E and then the integral of dA. Well, instead of having dA, you would just have E times A, being the area of the sphere, which is like the surface area, not like inside in a way, because that would be volume, not an area. But the area of the surface area of the sphere is 4 times pi times the radius squared. But we also know that the same flux is that the flux equals the flux equals u, like the u in the sphere, or the charge in the sphere, divided by epsilon. But if this is equal to flux and that's equal to flux, then they're equal to each other. And if we divide both sides by 4, if we divide both sides by pi, and if we divide both sides by the radius of the sphere squared, look at that. We're back at the same formula we were given A, which is 4 pi epsilon 0 q, which is the charge, over r squared. But you know how I said it was for like a point-like object? Like I'm a point-like object, but you can use that for other things. Like if you had a line like this, you could put like a cylinder around it. Well, the line was like one-dimensional instead of like a rectangle. You could put like you could put a cylinder around it, and then with that you could find like the electric field there, where it's not just a single point; it's like a whole line of points. Because a whole line of points would be different than just one point. If I have one electron, that'll produce a certain electric field. But if I have 500 billion electrons making a line, that's definitely going to produce a different field. So maybe you guys don't remember this, but if you do my physics class that requires it, maybe this will be a head start for you. So yeah, since I'm going to be a physics major in college, so I feel like maybe talking to you guys about like my physics stuff would be kind of fun. I think we're gonna win. Everything's gonna flow because it's the first area after all. This is like, hold up, hold up, that was too soon. 8 seconds. Why did it lie? Sorry, sorry, we're fine. Look, I already got messages infect enemies, and if you stand in them, oops, then they apply an effect to you. So these blue ones, see, okay, see my energy coming back fast because I'm maxed out region. So now every one one bah, oh my goodness. Every time 1 second passes, I get 7 energy back. But if I'm inside this thing, I lose energy because this drains energy. And it does add drains what I regain. So it actually like 15 energy per second, which is why even when I have this much reason, I still lose energy because of how strong it is. And the red one, it takes me down. Notice how my speed goes from 17 to 11.9. Like, this is me shifting. So I want to slow myself down. That's me being forced to slow down. And final area. Not every area, like boss area, has a big enemy. Like sometimes it's just a bunch of like a lot of enemies that are small. You have to like be careful of a lot of things, and it might get you in a way. And gee, that's one down. Okay, I could have done this back in 16 minutes again. Now I was explaining my physics stuff. And victory! I just passed Central Core 40 alone, and Central Core victory. And this would be the victory zone. See how it's like yellow, but this one's like a bright yellow. That's what happens when you're in a victory. And look, infinite pellets. I need so much XP where I don't even need it. Wish my ball. Oh, I love shooting ball. Never mind. That was me. I mean, what? Dude, who fabricated that AI clip? Who who could possibly have forged that a artificial intelligence created clip? Alright, but that's gonna be it for this one. I have a class to get to that's about to end in 3 days. And alright, see you later. Victory. Okay, bye.